guess we can start by reviewing the postulates that we got to in the first 3 lectures. So good morning, everyone. So what we have seen in the first 3 lectures, in the first 2, we derived this list of postulates that Galileo and Newton were happy with. And then we saw that some of those postulates didn't agree with Maxwell's theory of electromagnetism and the Michelson-Morley experiment. So we erased some of those and we added a new postulate. And then we ended up with 4 postulates, which are the postulates of special relativity. Einstein was a very philosophical guy. He didn't want to accept anything that he didn't need to accept. And this was the minimum set that he understood that he needs to accept. And based on this, we will derive all the theory of special relativity, and we will see that a new concept for space-time, a new conception of space-time, arises from these 4 postulates. So the first one says that there is a preferred class of frames called inertial frames, where the law of inertia holds, meaning free particles move in straight lines. And an inertial frame plus a choice of 0 for time gives you an inertial coordinate system, ICS for short. Then the third postulate tells us that the laws of physics hold in any inertial frame, all the laws of physics, mechanical laws, electromagnetism, etc. And they have the same form in any inertial coordinate systems. And finally, the last postulate says that in all inertial frames, the speed of light in vacuum is a constant independent of the direction of propagation and the speed of the source. Okay? So this last postulate in particular is crazy. And if you think a little bit about it, it tells us that either this is true or the Galilean transformation or addition of velocities is true. Okay? Both things cannot be true. All right? So today we will show how to start from these 4 postulates and how to construct the special theory of relativity. Okay? That's what we will do today. And we will start with 1 + 1 dimensions, meaning you have, let's say, space, 1 special direction plus the time direction. Okay? Because all the features that are important, they appear already if you have 1 special direction plus time, and later in the course we will move to 3 + 1, to 3 special directions. Now we see we will start today by deriving the Lorentz transformations. And the question we want to answer now is how are inertial coordinate systems related? Okay? So we have seen that they are, I told you that they are not related by a Galilean transformation. So the burning question is, how are they related? Okay? And that's the question we will answer today. So we will assume the manipulations to do this are really simple. They are like 2 by 2 matrices, basically. However, the consequences are astonishing. Okay? So we will have a lot of trivial statements that will lead to an astonishing consequence. And because of that, we will see this in 2 different ways, one today, another in the next lecture. So the problem we will consider, consider 2 inertial coordinate systems called O and O prime, okay? and such that O prime moves at speed v with respect to O. So the picture that we have is that the system O, let's say, is this system here. This is O, this is X, and this is T with respect to O. And then with respect to O, the system that O prime uses is moving at the speed v in the x direction. Okay, so this is O prime, and this is O. All right. So this is what O will see. O this will be static, and the system that O prime is using with respect to O will move at a velocity v. Is that okay? Yeah. Beautiful. So when they passed each other, so there is a time at which the axis that O uses and the axis that O prime uses, right, they overlap. So O and O prime overlap. So imagine I am O, I am standing here, and O prime is some of you moving at the speed v with respect to me. When we are at the same place, okay, we decide to set our clocks. So when O prime are at the same place, they set their clocks to 0. Okay? So T, O says, okay, from now on, this is T equals 0, and T prime is also equal to 0. Okay? And the event where they coincide, we will give it a name. This is called event E. So this, by definition, is the time at which O and O prime are at the same place. Okay? After this, after time 0, O prime moves with respect to O. Okay? Just imagine this is O prime, I am O, this is just moving like this at a constant speed. Okay? Of course, if we describe the things from the point of view of O prime will be standing from the point of view of my notebook, and I am the one that is moving in the opposite direction. Okay? So we can describe both from the point of view of O or the point of view of O prime. Is that okay? Beautiful. So events, O will use coordinates x and t, and O prime will use coordinates x prime and t prime. And our aim for today is to find x prime as a function of x and t, and and t prime as another function of x and t. Okay? So we want to say, if I am measuring something, right, when something happens, etc., like the motion of a particle, and I give to that particle coordinates x and t, what will the x prime, t prime coordinates be with respect to O prime? Okay? How do we relate our measurements of the same thing going on? All right? Beautiful. And notice that because they have set their clocks to 0 when they are at the same place, all what we are saying is that their origins coincide. The origins coincide. So in particular, 0 has to map to 0 in both coordinates. So g of 0, 0 is 0, and f of 0, 0 is also 0. This is just saying that the origins 0, 0 of O and O prime coincide. All right? Beautiful. So let's try to work this out. And let's use the postulates, okay? So good. So we have the first postulate. The first postulate tells us that the law of inertia holds. Okay? Yes?
So I was just going to ask, so in a classical sense, what are f and g? If we were to look at it from a classical perspective.
They are just functions. So they will be, it's just some function of x and t that we want to find. They are linear functions, actually. But yeah, it could be x plus t. It could be x squared minus t cubed. We are not saying much.
But if we model this from a classical perspective, is it the case that t dash is equal to t and x dash is equal to?
So in Galilean transformation, x is equal to x prime is x plus vt, for instance, right? So and t prime is equal to t. Yeah, that's a very good question. So if you have Galilean transformations, for instance, in Galilean transformations, yeah, thank you for the question. So if we have like completely classical sense, what time is it? Do you know the time? Perfect. Now, answer that question again. What time is it?
17 minutes past 11.
Yeah, sorry, now answer the question again. Beautiful. You see, your answer to the question didn't depend on whether I am moving or not. Okay? So, in Galilean mechanics, all systems, whether they are moving or not, they have the same notion of time. The time is the time, right? And that's it. We all agree. So, for instance, in Galilean transformation, t prime is equal to t. We all agree with the time. And because we are saying that by definition, because this is our problem, O prime moves at the speed v with respect to O, then in a Galilean transformation, x prime is equal to x minus vt. So for the case of Galilean transformation, the function f is this function, and the function g is this function. Okay? We will try to find now the relativity analog of this. Thank you for the question. Beautiful. Good. So the first postulate tells us that the law of inertia holds on both systems. Meaning, if O is a free particle that moves in a straight line, O prime should also see a particle that moves in a straight line. Okay? So whatever the transformations f and g are, straight lines in O map to straight lines in O prime. Okay? Because of that, the relevant change of coordinates has to be linear transformations. Very good. So, meaning x prime is equal to some coefficient alpha 1 x plus alpha 2 t, and y prime, and t prime is equal to beta 1 x plus beta 2 t, where alpha 1, alpha 2, beta 1, beta 2 are just constants that we need to determine. Okay? So these are constants that may depend on b, that will actually. on this relative velocity v. Beautiful. The second point is we are saying that O prime, so we deduce, so Galilean is this, okay? So so now we have deduced in relativity. We have a linear form, but it could be a bit more complicated. So it's alpha 1x plus alpha 2t, and t prime is beta 1x plus beta 2t. And the second point is that we are saying that O prime moves with velocity v according to O. So what that means is that the line x equals vt must map to the line x prime equals 0, okay? Because the system O prime, from their point of view, O prime is at x prime equals 0, okay? But from the point of view of O prime is just traveling in this line here because x is equal to vt, okay? So these are the coordinates of O prime basically with respect to O and with respect to O prime. So for this to be true, for this to map to this, it has to be the case, so this line needs to map to this, it has to be the case that x prime is equal to some constant that we will call gamma of v, x minus vt, while t prime, we cannot say much for now, okay? So this is just the information that with respect to O prime is traveling at the speed v, yeah? So that if you set x equals vt, this will give you x prime equals 0, and any time prime, t prime, we don't know. Now it comes the beautiful thing. Then we have the fourth postulate, okay? And here is where things become super interesting. With the fourth postulate, we will do the following. When O and O prime are at the same point, okay, when they coincide, we both send a beam of light, okay? In that direction, so light, and in that direction, light. And because of the fourth postulate, what I will see from my point of view of O is two beams of light, one in that direction, another in another direction, both moving away from me at the speed of light c. But O prime, from their point of view, even though they are moving with respect to me, they will also see exactly the same. Two beams of light moving at the speed c in that direction and in that direction, okay? That means, in other words, in equations, that the line x equals ct maps to the line x prime equals ct prime, and the line x equals minus ct for the other beam has to map to the line x prime equals minus ct prime. Is that okay? Any questions about this? Yeah? Beautiful. So what we are saying is, let's imagine that I described this beam of light, right? So I am describing that the coordinates, these coordinates of this photon as it moves to the right, right? So that's what I described. So from my point of view, from the O point of view, I say x, how can I say that? I can say, for instance, that the speed of light, c, for that photon, you can compute by saying x divided by t, okay? But from the point of view of O prime, what they would do is that they would say that c is x prime divided by t prime, okay? So, but we know that x prime is gamma v x minus vt divided beta 1 x plus beta 2t, and this is true provided x is equal to ct. So if you take this and you plug x equals to ct, you need to get the speed of light, okay? And that gives you conditions on gamma v, beta 1, beta 2, and v. Is that okay? Is that understood? Beautiful. So the two equations, you get two equations, one for each light ray, is gamma v ct minus vt equals c beta 1 ct plus beta 2t. And another equation is that minus ct minus vt is equal to minus c minus beta 1 ct plus beta 2t. This is just a statement that the light beam moves at the speed v with respect to both systems. We are almost done. You can solve for beta 1 and beta 2 if you use these two equations. And what we find then is that x prime is gamma v x minus vt, and t prime is gamma v minus v over c squared x plus t. Beautiful, almost there. So we have derived the transformations, the Lorentz transformations, up to a constant gamma v that we will determine momentarily. Any questions about the manipulation so far? So we just use the fact the origins agree, the transformations have to be linear because the systems are inertial. O prime is moving with respect to O at velocity v, and then both they describe these beams of light as moving at the same speed c, okay? And that's all we have done. And then we derive this. Now, there is another trick, a very nice trick. So imagine now, so this, let's call it equations, system of equation number 1. Imagine now that you want to consider a slightly different problem, the opposite problem. You want to write x as a function, prime let's call it, of x prime t prime, and t as a function of x prime t prime. What this means is, now we are going to solve the inverse problem. We are going to say, imagine that we have x prime and t prime, so from the point of view of O prime, and then from that we want to compute what x and t are. this is the same problem we have already solved, but you replace v by minus v. Because with respect to O prime, O is moving at the speed minus v. Okay? So this is the same problem. With v replacing minus v. So if you do this, the solution we will find is that x is equal to gamma minus v, x prime plus vt prime, and t is gamma minus v, v over c squared, x prime plus t prime. So it is the same solution as solution number 1, but we exchange the xt by x prime t prime and v by minus v. Okay? Because from my point of view, O prime is moving at the speed v, but from their point of view, I am the one moving at the speed minus v. Okay? So far, so good. Any questions? Beautiful. So now we can do the following trick. We can take equation 2 and replace it into equations 1. Okay, so you just take these two expressions for x and t and plug them into equations 1. And that should be a true equation for all x prime and t prime. And if you do this, you obtain a beautiful equation that gamma v, gamma minus v, times 1 minus v squared over c squared has to be 1. Okay? And now there is another point, and we would like to claim that gamma v is equal to gamma minus v. Meaning, this factor that we are looking for, it depends on the relative speed, not the velocity of the two systems, okay? But it depends only on the speed, the absolute value of v, and not the sign of v, okay? And here there are three approaches that you can do. Some books tell you that this is an assumption, and that's it. Or you can do a change of transformation, which is called parity, and you take x to minus x tilde, and that is a bit complicated. But there is a better argument, which I just saw actually in the shower, and it has to do with the isotropy of a space. And because this is like a nice lesson for you guys, I thought I would explain you why this is the case. So isotropy of a space means the following. It means that if you are in vacuum, all directions, imagine you are in vacuum in the universe, all directions, they look exactly the same. Okay? And the space, time more precisely, but space, is the same in any direction that you look at. Okay? Now, when I told you that I was going to describe things in one special dimension, when we say that we will choose one special dimension, of course, what we are doing is the following. We are in space-time, right? We pick one random direction, and I declare that this direction is the x-axis. Okay? And then we do this computation using that this direction is the x-axis. But of course, I could have used, my arm is the x-axis. Do you all agree I could have used this direction instead? Why not, right? You are in a space, you could have used in this direction. Or you could have used this direction. and you would have obtained the same gamma v. But also, you could have used this direction, which is the opposite as the one we started with. Okay? So all these directions, they should give you the same gamma v. In particular, this direction and the opposite direction. And because of that, gamma v cannot depend on the direction of the velocity, but it depends on this. And this is true. Okay? But this is very cool, because then we solve for gamma, all right, and is a square root of 1 over 1 minus v squared over c squared. This is called a Lorentz factor. It appears everywhere in a special relativity. If you need to memorize one expression, memorize that guy. And with the Lorentz factor, we have found our final version for the Lorentz transformations. So we will write them here. Lorentz transformations. So x prime is gamma x minus vt, while it is customary to multiply t by c. So ct prime is equal to gamma ct minus v over cx. Sometimes it is useful to have the inverse ones, so that x is gamma x prime plus vt prime, and ct is equal to gamma ct prime plus v over c x prime, where gamma is what I just wrote, square root of 1 over 1 minus v squared over c squared. Okay? So this is the way that inertial coordinate systems are related in a special relativity. Okay? There is a lot of fascinating things about this. So first of all, one technical thing, you can write this as matrices in terms of 2 by 2 matrices, and sometimes you will see them written like this. So ct prime x prime is equal to gamma 1 minus v over c minus v over c 1 ctx, or the inverse. And something fascinating about these transformations, they are a bit more complicated than the Galilean ones, which were something very simple. But notice that in the limit in which v over c goes to 0, gamma goes to 1, and you do recover the Galilean transformations. So the Galilean transformations are obtained as a limit as the speed, our speeds are smaller than the speed of light, much smaller. So that if the speeds are smaller than the speed of light, much smaller, then you can still use Galilean transformations. So that the special relativity corrects Galilean transformations, but these corrections are important only when the speeds of objects are kind of the same, similar to the speed of light. However, they are different, and this is what they are. Okay? Any questions? The most beautiful feature of this, and let me write down. Let me ask. Let's solve a little problem with this, which shows how crazy these transformations are. Is that space and time are kind of intertwined and connected. So you cannot separate them, and you can only talk about space-time as a thing. Okay? And let's try to solve a very cute little problem. That will make that manifest. Something that we have in Galilean transformations is the concept of simultaneity. Okay? So if two events happen at the same time, every inertial system in Galilean or Newtonian mechanics will agree that these two things have happened at the same time. This is not true anymore now. Okay? So let's try to see an example where two things happen at the same time for one system, but happened at different times for another system. Okay? With numbers. Let's put numbers. Okay? Beautiful. So the problem is the same. It's the following, sorry. So imagine that in a given ICS, two simultaneous events are separated by 4 times 10 to the 7 meters. This is as basically the distance between two opposite points in the equator of Earth. Okay? So on Earth, that's how far you can get, as far as you can get. This is it, right? And then we have a second ICS moving with respect to the first at speed v equals 3 times 10 to the 4 meters per second. Okay? Remember that light is 3 times 10 to the 8, just for reference. And this, for reference, is basically the speed of Earth in the solar system, okay, with respect to the sun. So Earth is moving at that speed. So it's just some numbers. So one system tells us that there are two events, poof, the explosion of something, the birth of two people, whatever, right? They happen at exactly the same time. But another system is moving at this speed. So what will the other system see? Let's see. Beautiful. We just have these tools that we have derived, right? So let's call the first system T prime and X prime, right? And the coordinates for the events let's say that in my time, they happen at t prime equals 0. So this is the first reference system. And they happen at with the following coordinates. So the time is 0, and the distance is x prime 0 for the first event. And for the second event is x prime plus d, okay? Where this d is 4 times 10 to the 7 meters. All right? Beautiful. Then the second system will say, well, with respect to me, if I want to find x and t, I could use these transformations here, okay? I want you to use the inverse, but it's just this transformation here, all right? So you take these transformations, you plug t prime equals 0, x0 prime for the first event, and you plug t prime equals 0, x0 prime plus d for the second event, okay? And what Tx will see, what O will see, is that Ct1 is gamma v over c x0 prime for the first event, but for the second event, this is gamma v over c x0 prime plus v. And behold, they are different, okay? So you can ask, how different are they? So T1 is different from T2, and you can compute the time difference, which is just T2 minus T1, and this for large speeds, for a small speed, sorry, is gamma v over c squared d, which is 0.00001 seconds. Okay? Really small, really hard to measure, but non-zero. Okay? So two things that are simultaneous with respect to one system, they don't have to be simultaneous. In general, they are not, to a second system. This is crazy, right? I mean, people were mind blown by this. Even more, actually, you can find examples where I will think that A happened before B, but if you are moving fast enough, you will think that actually B happened before A. So even the order of things can be reversed in a special relativity. Okay? Any questions about this?
How do you arrange for the order to be reversed? That doesn't seem like, if I generalize D, I mean, what, you want to make D negative?
Right. So you could play with x0. So you have to play with t0 and x0, and that will be more clear. Actually, it is very clear in what I will do in a bit with diagrams. But you will have problems in the problem sheets where you show this. Sure. But you have to play with all the coordinates. Yeah, you're right. Because from this, it seems this goes away in the difference, and this always have a given sign. Yeah, that's right, yeah. Now, in general, you need to imagine that there is a D1 here, and that the time is different, okay? So if the time is different, because they are not simultaneous, then you have like 0 here and something positive here, but then you need to plug this, and you can see whether you can adjust things, yeah. Beautiful. So the last thing I will be telling you today is a nice thing, a nice idea to draw things in a special relativity, and it's the concept of space-time diagrams. And we have already seen a little bit of this, but let me tell you a few things. So basically, in order to draw these space-time diagrams, let's say we choose O with coordinates x and often instead of t, you use ct or ctx in the order given by these transformations. And then in an axis, you draw x in one axis like this and ct in the other axis. Okay? And then you use the same units, or better to say, the same scale. Okay? For instance, if you use years to measure your time, you need to use light years to measure distance. Or you could use seconds and light seconds, inches, light inches. You need to use them in the same scale. Okay? In this way, if you use this scale, in my coordinates, in these coordinates, a rate of light will always be traveling at pi over 4 or 45 degrees. Okay? So with these beautiful coordinates, light will be traveling either like this, right? Or if it is light in the opposite direction, sorry, this was supposed to be 45. It's traveling like this, okay? Where this angle at pi over 4, which is 45 degrees, okay? In addition, imagine that you have this plot, and there is another observer. With respect to me, this observer is traveling also at a constant velocity, okay? And this constant velocity, let's say our origins agree. Let me use another color, green. So this is light, and this here is O prime, which is another observer. Notice that we will always have, and we will prove that other observers, they can never travel at a speed higher than light, so that their slope is always above the slope of light, okay? So all the particles, the trajectories of the particles will always be inside this cone, okay? Because this is how fast light can go, and never, nothing can go faster than this, all right? So there is something else that sometimes we like to plot. And for instance, if you have a system O prime, and by that means the origin, so that this line is the line x prime equals 0, in the same system, you could draw the line t prime equals 0. Okay? Beautiful. So whenever you have an observer, whenever you have these space-time diagrams, the lines of O prime will always be straight lines that are inside this cone, and the lines t prime equals 0, etc., will be lines here. And something that is cool is that this angle and this angle is always the same. Okay? So that we have this, this nice symmetry. So basically, all we are doing is a very simple representation. Is we are choosing the units right, and we are just plotting the trajectory of things into this diagram. But the beautiful thing is that because light moves in these 45 degrees angles, and we know things cannot go faster than light, we will prove that, particles, etc., they can never cross this kind of cones, okay? And that's something very useful. Is that okay? It's, yeah, it's just a diagram, and the more you use them, the more use you will get to using them.
Did You say t prime equals 0, it must be an exact reflection.
Yes, so basically, yes, that's right. So if this angle, thank you, is, let's say, alpha, this angle should also be alpha. Or if this angle, so the point is, right, so the point is that all observers will agree that this is light, right? So that this red line should always be in the middle of these two axes, in the middle of these two axes, and so on, because all observers agree that light is at kind of 45 degrees. Is that okay? And this, of course, looks squeezed like this because of the factor gamma. Yeah, and the faster the observer O prime goes with respect to O, the closer this will get to the light from our point of view, from the point of view of O. Is that okay? Any other questions? Beautiful. So give me one more minute and then I will let you go. The second way that we will have to derive the Lorentz transformations, of course we will get the same result. It is something that Einstein introduced, and then people kind of, now we think of physics in that way, but it's something extremely deep and extremely important philosophically. How do we measure things? Okay? So the question that Einstein asked was the following. Okay, you tell me that you will assign coordinates x and t to events, and in Galilean transformation, we somehow assume that we all have this infinite ruler, right? And with this infinite ruler, we can see the location of things. But that's not true in a special relativity. It cannot be true. So first, Einstein devised a way to measure positions of particles, etc. And then with that way, he derived the same equations, okay? Which I think is beautiful. So basically, we will derive and revise the paper by Albert Einstein in the next lecture. Anyway, thank you very much.